video that we'll be making describes the register file. So it uses a decoder actually that uses instruction bits 0 and 1, which correspond to the destination register bits for either taking out of SRAM or taking the output of the ALU and putting it in the register file. And so this basically tells us decoder 0 through 3 tells us whether we want to write to register 0, 1, 2, or 3. And so we take the clock and we look at instruction bit 8, which tells us whether we're going to need to write to the register file or not. So this is basically like a clock enable bit, which tells us if we're going to write to the register file at all. So that's just an AND gate. And then there's all these AND gates here that take basically the clock enable bit, whether we're going to write or not. And also basically the location from the decoder, which register we're going to write to, and it ANDs all of these so that it enables one of these clock bits. And these clock bits get fed, so clock 0 gets fed into register 0, clock 1 to register 1, etc., etc. So they'll basically tell us which register we're allowed to write to. And then we have this 8-bit mux, which I've explained multi-bit muxes in another video, so I'm not going to do that here. But it takes the SRAM output and the ALU output, and instruction 6, which is the data source, I think, bit, tells us whether we want to write the output of the SRAM or the ALU to the register file, and it puts that in at the 8-bit input. And then all of these different clocks that we generated using the decoder and the instructions get fed in as well. Inside the register file, we just have 4 registers, and they each have their respective clocks, which enables whether or not we can write to a given register at a time. Only one of these clock signals is enabled at a time, so we only write to one register at a time. The same input is fed to each register, only gets written when the clock is enabled, and then we have the outputs of each of the registers sort of hanging out here. Inside each register, it's an 8-bit register, and so we need to be able to store each of the 8 bits, so we need 8 flip-flops here, basically. And they use the clock signals, which are unique to each register, to trigger data transfer into the flip-flop, basically. And these data bits correspond to the input to the register. This is the 8-bit input to the register file that comes from the SRAM or the ALU. And we know how flip-flops work already. What's unique about these flip-flops, I guess, could have said this in the PC video as well, but they need a slow inverter from clock to clock bar to make sure that there is, at some point in time when the clock transition happens, clock and clock bar will have the same value and D can pass through to the latch portion of the circuit. We've explained the flip-flop in another homework, so I'm not going to go into too much detail. But there is more buffering here on this clock bar output to increase the delay between clock and clock bar changing, so that we can get the necessary amount of time needed to correctly write a new value to Q. So the register is just those 8 flip-flops in parallel, and the register file is just 4 registers. And then we have these 2 muxes here on the outputs of the registers that tell us based on the instruction bits 2, 3, 4, and 5, which are like your register selects A and B, which registers we want to use in our calculations for the ALU or to store to SRAM from register select A. So I think that's high level how the register file works. Again, I'd probably use transient simulation here, switching which clock bit is enabled, as well as the data that's being inputted to the register file, and then checking to make sure that each register either stays what it was before if its clock is disabled or changes to the value on the input when its clock is enabled. That's how I would do that.